Okay, let us begin. So today, you all get to do a Newton-Raphson load flow, and it's multivariable Newton-Raphson, right? Because we have multiple equations that we're going to write and multiple variables we're going to solve for. So the first thing we have to do is figure out what equations to write. And then the second thing we need to do is figure out what we're going to solve for, what variables we're going to solve for. So I already put this in the whiteboard. I have our system. And I have the two required equations that we need to be able to solve those f of x equations, okay? So I'm not going to bother writing the partial derivative approaches. Can you know how you have to do the partial derivatives one? And there's some automatic equations that I provided in the lab. I find that it takes more time, especially for simple systems like this, or relatively simple, I should say. So I'm not going to do the partial derivative just by using the equations. I'm actually going to do partial derivatives, actually doing partial derivatives. Not too complicated, but we'll go from there. So remember what our steps are, right? So we'll say step 1, ID bus types. And the 3 bus types are slack, gen, and load, or reference, PQ, and PV. We know the slack bus over here. That's already called out. Over here, we know the magnitude of the voltage as well as the power injected into the bus. So that is a PV or a gen bus, right? Because you know the real power and the voltage. For bus 3, all we know is P and Q. So that is a load or a PQ bus, right? So once we have our bus types, now step 2 is ID the equations. We have 3 of them. We're going to write an equation for delta P2 because we can, right? We can write an equation to see if our power balance matches what we inject. We can also write a power balance equation, a real power balance equation at bus 3. And we can also write a reactive power balance at bus 3. Okay? So we know our 3 f of x equations that we need to write. So we got step 2 done. Step 3, identify the variables, right? So we're going to ID unknown variables. And remember, these variables aren't just plain variables. They are our state variables. These are the ones that once we solve for, we'll be able to fully characterize operation of our system or the state of the system, if you want to put it a different way. So our 3 unknowns, we don't know theta 2, right? It's not specified. We don't know theta 3, nor do we know V3. And again, keep in mind that with my voltages, when I'm doing power balance or load flow, I'm not going to include the absolute value because it just makes the equations get really busy and messy. So as long as you all keep in mind that the absolute value of V3 is intended when I write V3 here, then we're all on the same page. So these are our X equations. We're almost ready to actually start solving or writing our power balance equations, but I didn't give you enough information, so you have to solve for Y bus, right? Got to have Y bus first to be able to get any power balance equations. So my Y bus, and this one's pretty easy, right? Because you can see I already have inverted the elements because it says Y12. So I'm going to move the J out there to factor. So that's 40 plus 20 negative for the self-admins. The off diagonals from bus 1 to 2, is plus 40. The off diagonal for bus 3 is plus 20. And because it's a symmetric matrix, we can go ahead and just copy those down. We don't even have to look at them. Now we can do the self-admittance for bus 2, minus 40, minus 20, minus 60. And then the admittance between bus 2 and 3, the negative of it is 20. And then lastly, we have to do the self-admittance for bus 4. And that's just the two elements added together. Okay. Looking at Y bus, we can make an assumption or a calculation. Don't even have to make an assumption. We know that G for all cases is going to be equal 0 because there are no real parts. So my suggestion, if you're still not sure, I'm going to cancel out anytime I see my G term, right? Because I know it's multiplying by 0. So I don't care what the cosine of theta ik is equal to, because I know for all GIKs, cosine of theta times 0 is 0, doesn't matter. Or sine theta ik times GIK is always going to be 0. So I'm not even going to bother writing that part of it. I'm just going to completely ignore that. Okay? And my B, because that's all I need, right? All I need is my susceptances, minus 60, 40, 20, 40, minus 60, 20, 20, 20, minus 40. Okay? So I've got my Y bus. Well, not only do I have my Y bus, I also have my Y bus broken down into real and reactive parts. So I've done step 4. Now I can write my power balance equations. Oop. Okay. So I can see I need delta P2. Notice that I here, and if this is helpful, write I is equal to 2 when you're doing your summations. That's going to equal V2. Now I'm inside my summer. VK, K is equal to 1. So V1. Now there's 2 ways to do this. You can either write B21 like that, right, if you want. Or if you want to make it a little easier, I can see that B2, row 2, column 1 is equal to 40, right? So either way, you can substitute in your value for B there if you want, or you don't have to. You can just leave it as a variable. It really just depends on what's easiest for you. So I'm substituting in to make it hopefully a little more obvious to see. Do you prefer that, or do you want to see the B21 in there? Your choice. B21. B21, okay. B21 is here. And then that becomes sine of theta 2 minus theta 1. That's the first one. Now I increment to 2 plus V2, B22, sine of theta 2 minus theta 2 plus V3, B23, sine theta 2 minus theta 3. That's it for the summation. Now I'm going to subtract from that P generated minus P delivered. In this case, I've got power going out, and we're going to say that S base is 100. So that is minus, plus. So it's minus a minus becomes plus 5 per unit power. That's my first power balance equation. Questions on that? Any questions? Going too fast? Just right? Awfully quiet.
Paul, I have a question.
Yes, go ahead.
Where did the 5 at the end of your equation come from?
Because I have minus P generated minus P delivered. So minus a minus becomes a positive 5. I've got 500 megawatts being, oh, sorry, you're right. Not 5. This is bus 2. Becomes minus 4. Is that what you were saying?
Yes, thank you.
Yep. Should be 4 because I'm at delta P2, not delta P3. So that's minus 4 per unit power. That's generated at bus 2. Any further questions on delta P2? Because we can go right to delta P3, right? Same process, I is equal to 3, V3 times V1, B31, sine theta 3 minus theta 1, plus V2, B32, sine theta 2 minus theta 3 minus theta 2, plus V3, B33, sine theta 3 minus theta 3. And now I'm adding the PG minus PD, which is positive 5. Last one, delta Q2, or delta Q3, sorry, where I is equal to 3. Now I have to use a different equation. So you'll notice when I did my delta P3 equation, I could go through it pretty quickly because they have the same form, right? I'm just making I equal 3. So anytime I see an I just put in a 3 and it goes much faster. And you can see they have a very similar form. The delta Q3 is a new equation, right? So I just got to go ahead and start from scratch. So this is going to be V3 times my summation, V1 times negative B31 cosine theta 3 minus theta 1 plus V2 minus B32 cosine theta 3 minus theta 2 plus V3 minus B33 cosine theta 3 minus theta 3. Then I subtract from that QG minus QD, which becomes plus 4. I've written my 3 power balance equations, but it greatly benefits me, if I can go ahead and substitute some numbers out of here. So I'm going to do that. And let's see, I've got V2, 1.05 times V1, which is just equal to 1, right? Times B2, well, actually, do I want to do it that way? See if that's going to confuse people. I'll write it this way. Now I'll substitute in for B21. That's 40. Now I have sine theta 2 minus theta 1. Well, theta 1 is always equal to 0. So that becomes sine theta 2 plus V2, which is 1.05. B22, which is minus 60. Now I have the sine of theta 2 minus theta 2. That's always going to be equal to 0, right? So sine of 0 is equal to 0. So that middle term goes away. And plus V3, B23, 20 sine theta 2 minus theta 3. And then I subtract 4. So I'll finalize all this up, make it easier. This becomes, let's see, 40 times 0.05. I think that's 42. Sine theta 2 goes away to 0. And then that becomes 1.0. So that's 20.5, I believe, or 20.1, sorry. No, 21. Right, do I have it right? Let's see. 5 times 20 is 100. So move over 1, that becomes 10. Yeah, so it's 21 times V3 sine theta 2 minus theta 3 minus 4. That's my sort of simplified down as much as I can equation. Okay, can't get any more simplified than that. Do the same thing for my next equation. I have V3, which is still a variable. This is just 1 times B3, 1, which is row 3, column 1, 20. Sine of theta 3 minus theta 1 is just sine of theta 3. Plus V2, which we've already said is 1.05 times B3, 2, 20. Sine of theta 3 minus theta 2. Can't simplify that down anymore. And then plus V3, B doesn't matter. This goes to 0, right? So that becomes plus 0. And that goes to 5. So I have 20 V3 sine theta 3 plus 21 V3 sine theta 3 minus theta 2 plus 5 is my second power balance equation. My last power balance equation, V3 times 1 times minus B3, 1, negative 20. That just becomes the cosine of theta 3. Let me know if I'm going too fast, right? Because we've done the fact that theta 1 is equal to 0. So hopefully we can recognize that pretty quickly here. So this becomes 1.05 V3. I hope it's 1.05 and not, yes, 1.05. I'll get myself confused. Actually, 1.05 times V2 times negative B3, 2 minus 20 cosine theta 3 minus theta 2. And lastly, I have V3 times negative B3, 3, which is a positive 40, times the cosine of 0 is 1. And that goes to be plus 4. Now we simplify that down. I have negative 20 V3 cosine, whoops, cosine of theta 3 plus, why did I write V2 over here? That is V2. So this becomes minus 21 V3 cosine theta 3 minus theta 2. Plus, now I have two V3s, right? So that becomes 40 V3 squared plus 4. So my final three equations, I'm going to write those over here. Delta P2 is equal to, is equal to 42 sine theta 2 plus 21 V3 sine theta 2 minus theta 3 minus 4. Delta P2 or delta P3 is equal to 20 V3 sine theta 3 plus 21 V3 sine theta 3 minus theta 2 plus 5. My last power balance equation, negative 20 V3 cosine theta 3 minus 21 V3 cosine theta 3 minus theta 2. And then plus, I better clean this up because once I start taking partial derivatives, I won't be able to make out. That's minus theta 2 plus 40 V3 squared plus 4. Those are my three equations. Any questions on how I got those? Feel okay so far? All right, so we've got our power balance equations. Now, step 6 is find the Jacobian, right? And so recommendation on the Jacobian is to identify rows and columns so you know which partials you have to take. So we know the Jacobian has the rows as shown, and the variables, theta 2, theta 3, V3. So I know I have to take the partial of delta P2 with respect to theta 2, and on and on and on. So let's start doing those here. So the partial of, I'm just going to write P2 with respect to theta 2. Hopefully you all can see that pretty quickly. 42 cosine theta 2 plus 21 V3 cosine theta 2 minus theta 3. And that's it. I do the same thing for the partial of P2 with respect to theta 3. There's only one theta 3 in this expression. So when I do the derivative, I have minus 21 V3 cosine theta 2 minus theta 3. And my last one is the partial of P2 with respect to V3. And let's see, that's going to give me 21 sine theta 2 minus theta 3. The Jacobians are not hard to find, and they usually are a little simpler than your power balance equations. So that's why I find it's easier just to take the partial, especially when I've only got, if I've only got 3 or 4 equations and 3 or 4 variables. I find once I simplified it down, they're pretty easy partial derivatives to take, in my opinion. Let's do the partial of P3 with respect to theta 2. All right, so that's going to be equal to, here. So that's going to be negative 21 V3 cosine theta 3 minus theta 2. It's our first equation. Our second equation, this is P3, with respect to theta 3. That's going to be 20 V3 cosine theta 3 plus 21 V3 cosine theta 3 minus theta 2, and that's it. Last equation, delta P3 with respect to theta 3. No, V3, got it right. Okay, let's see. So I have 20 sine theta 3 plus 21 sine theta 3 minus theta 2. Okay. 3 more partials. We're almost done. Partial of Q2 with Q3. No, yeah, it's Q2, sorry. With respect to theta 2. Wait a minute, that's Q3, right? Not Q2? Sorry, folks. I wrote down, why did I write down Q? It should be Q3 right here, sorry. That's Q3. And this is Q3. The equation should be correct. All right, so this becomes the cosine, the derivative of cosine is negative the sine. So that would cancel out the negative in front of the 21. But I'm taking the derivative of the negative theta, so that becomes negative 21 V3 sine theta 3 minus theta 2. That's it. That's the only one that has theta 2. The next one, partial of Q3 with respect to theta 3 is equal to positive 20 V3 sine theta 3. And then this is going to be plus 21 V3 sine theta 3 minus theta 2. And that's it. And then the last one is Q3 with respect to V3. That's going to be equal to minus 20 cosine theta 3 minus 21 cosine theta 3 minus theta 2 and plus 80 V3. Okay. Everybody following along so far? Or am I going too fast? A little fast? Okay. I'll pause so that you can write these down and then you can ask any questions. But really, so far, all the derivations, all the work that we've done is to obtain these 12 equations that we need. We had to write 12 equations and then we had to do 9 partial derivative. So we have 12 equations that we have to solve for when we have 3 unknown variables. I'll give you a few minutes to get caught up with that. Everybody caught up? More or less? Well, again, we can come back to that in a second. So for those of you who are ahead, what we'll do is we'll check off another step, right? We found the Jacobian. Now, step 7 is do NR algorithm, which means, so we got to do a little bit of setup, right? Now, this just depends if you're doing it in your calculator or not. I'm going to assume if you're doing it in a calculator, so you just have to iterate until you're satisfied. So I'm going to go ahead and check. So you're going to plug in to your f of x equations. You're going to plug in delta P2, delta P3, and delta Q3. You're going to plug in your unknown variables, right? Theta 2, theta 3, and V3, 0, 0, 1 for all of those. And do they equal 0? If it's yes, you're done. At least in terms of Newton-Raphson, because you got the right angles and magnitudes. If not, then I'm going to go over here. We're going to go ahead and solve for delta x. Delta x is going to be equal to our inverse Jacobian evaluated at our 0, 0, 1. Multiply that by our f of 0, 0, 1. And then x for the next iteration, we'll call it next, for lack of a better term, is equal to your x, actually we'll put the negative up front here, plus our delta x. Now, go back and start over again. It's the same process. Check if f of x is equal to 0 with the new values that you calculated. Yes, you're done. No. All right. So now these here, I'll put or x next. If it's not, solve for delta x by plugging in those values for your variables. Rinse and repeat, update your x values, and then go ahead and check again. If it's finally done, find any required PIs, P injections, and QIs. That's it. Because the lab handout said, whoop, sorry about that. It basically just said, update the bus voltages. That's all you need to do. You don't have to solve for any PIs or QIs. It's sometimes good to check, did I get what I expected to see if like the total power in your system matches. You can certainly do that. You can also see if it makes sense to look at bus magnitudes and angles and see if the real and reactive power flow go through there. Then answer a couple questions. How many iterations did you need to do to get within tolerance? Is there anything you could have done to simplify your work? Do you remember how we looked in class last time and we just focused on the Jacobian and using those partition matrices to kind of do it really fast, that super fast approach? That might be able the way you simplify your work. It might take a lot more iterations, but you might be able to get close enough doing it. It just depends on your system. And then can you examine the effect of reactive power flow on bus voltage without completely redoing the Newton-Raphson approach? Remember we talked about sensitivities and how sensitive a reactive power flow is to a voltage? That's told to you by the Jacobian. So you should be able to do that. I will bring up my script, and not for you to cheat, but I'll put an absolute error of 1 times 10 to the minus 3. And remember, here's clear CLC. There's nothing up my sleeve, right? No built-in stuff in MATLAB, and I'm cheating. So I did all that stuff, and I didn't do any simplifications, right? You can see I kept B's and B's all in there. I didn't take any shortcuts, so this is a lot more work to write it out. But hopefully it runs and doesn't crash. Let's switch over to, I didn't hear a ding. And I actually calculated a lot more. I did that. Would allow me to move. So you can see all the data. And it took, to get to that count, it took 3 iterations for me to get to within 0.1% error. And again, I like to sanity check my work. Real power injected is 1 at bus 1 and 2 at bus 2, which is good, right? Because bus 2 is a generator bus and it's supposed to generate 400 megawatts or 4 per unit power. But I actually did the calculation, and the sum of the real power injected in bus 1 and bus 4 equal the power demanded at bus 3, right? So I'm feeling pretty confident in my results because I can show you in my script file, I didn't cheat. I actually wrote the power injection equations for all the buses. So I didn't just say it's equal to 4 and 1. I actually did all the calculations. Like I said, I'm not a magician, nothing up my sleeve. It's just brute grinding. I've been yapping for 35 minutes. You're probably sick of hearing me talk. Questions? Yes, sir.
So when we're doing this ourselves, because like in your pre-lab video and the shown here has all the work and the MATLAB script done out, how much of that are we allowed to like just copy?
Well, you used the wrong expression.
Doing our own work.
How much are you allowed to copy? I'm not asking you to copy. I'm showing you what I'm doing so you can actually hopefully learn how to do this. I don't want you to just write down and just turn in what I said. I mean, you can do that, but you're going to pay a price on the exam. So my expectation is you see what I've done. It makes sense. You can replicate the work and then you can check it. Because if anybody's been doing this homework to the point, it's easy to make mistakes. So one of the things that I'm trying to do is not have you spend 8 hours and you can't get it to work because you have a sign change or you forgot a 4 multiply. So I'm showing you all this for you to check your work. Never copy, do your own work and check it. I have to believe that you all are pretty much seniors and that you'll do what is necessary to make sure you understand it. If you copy the work, that only hurts you in the long run. So I don't want you to copy anything. I want you to check it and do your own checks. That make sense?
Kind of, I was thinking, even if we do it ourselves, our final script is probably going to be very similar to your script
Well,
if we're doing it.
it's okay, but like you don't have to use deltas for angles.
But
You don't have to use
now that I've seen you do it, the first thought in my head is, oh, that's so convenient. Why don't I just do it the exact same way you've done it?
well, in the past, I used T1, right? I didn't use delta, I used T1. You could call it your name if you want it. You can call it the variables I'm using, like I'm using very specific variable names because it has a little bit of more information and in-depth information. So I'm trying to set you up for maybe perhaps future learning, what that delta means. But like iter count, I've used n in the past. My hope is that you don't use exactly the same variables, but that's not required. I just don't want you to copy it. And if I see exactly the same variables, it's like, okay, well, you just copied my work. You should be able to, and also this is the MATLAB script file. In reality, what I did here is not the MATLAB script file, is it? I have much simpler equations in here than MATLAB. But again, because this is so prone to making simple math mistakes, you know, I've had people come to me and I spent 40 hours on this homework and it still doesn't converge. I'm trying to avoid you doing it. If you want to do that, that's perfectly fine. You can pretend you didn't see any of this stuff and go cranking. But I mean, I've done this because even when I've written some of this code, sometimes I've spent hours and hours and hours and I'm pretty proficient at it. And still, you just type in a negative when you meant positive. It's easy to make little typographical errors. So I'm not trying to have you focus on, okay, here's a typographical error. It doesn't converge. All right, let me look at what Paul's first iteration result is. It matches mine or doesn't. And now I need to focus on one specific area because it's just a lot of material. That's all. That answer your question? B.
From what you say, are we submitting the MATLAB time?
Do you remember what I said last class? You don't remember? What I said is I don't really care what your MATLAB script looks like. It's fine to do it. I want to see your process. Because in a test, if you say, all right, here's the answer to problem number 1 on the test, it's all a MATLAB script, you get 0 credit. Because I don't care if MATLAB knows how to do it. I want to see that you do it, and then you do it on paper. MATLAB is a calculator. That's all it is. I'm using my MATLAB script here to calculate stuff. All the work that went into doing that is all in here, right? That's all the work that I've done. So as a result, that's what I want to see. I don't want MATLAB script. Does that answer your question?
Yeah.
I think you had the question first.
Do an test here to have us actually solve those?
Possibly. Possibly. If you can do it in MATLAB, if you do it in MATLAB, right? You can run 5 million iterations in 30 seconds. Then if you're going to use a calculator, just give me the results after 1 iteration. If I say, find the voltage at bus 2, I'm not gonna say do 4 iterations, because that's just busy work. I just want to see if you know how to calculate the numbers correctly, so I want to just see 1 iteration. What do you mean by stupid calculator? I didn't ask you to do iterations. I said do 1 iteration, which is do it by hand. Enter the numbers enter the numbers in by hand, and then show what the results are. You don't understand what I'm saying? Yeah. Just like if I said, hey, would you tell me what, I have a question for you. Tell me what 42 cosine theta is, theta 2 plus 21 V3 cosine theta 2 minus theta 3 is. If you knew what theta, if you had a number for theta 2, theta 3, and V3, you should be able to tell me that number, right? Entering it in your calculator. You don't think you could? Yeah, you should be able to, right? So that's what you do in your calculator. In MATLAB, you're doing the same thing. You're just giving it variable names so that you can update it each and every time.
So everything that we just did, this is the work, and then, you know, the answer from that lab would be less the final, or like, would that be enough work to get full credit?
Yes, if you wanted to show me the MATLAB script, sometimes that's a nice thing. And it also is good for you to keep the material together.
Yeah.
What I'm saying is if you just give me the MATLAB script, you don't get credit. If you add it in there after all your work, that's great. I don't have any issue with that. That's encouraged, just so you can keep the material together. But I won't give you credit if you just give me the MATLAB script. Yes, sir. It's all the same. It's just Newton-Raphson. It's just different locations and variables and stuff like that. That's all it is. Yep. And that's why if you look at the process, the 7-step process, that's the same process in the lab, in the homework. It's all the same. There's no differentiation. You got to do that 7-step process. And technically it's an 8-step process, right? We'll have to put 8 up here. Where I said find, missing, desired, PIs, and QIs. Okay? Yes, sir. Any questions in TV land or in-person land? Because I will pause the video. Now, it's up to you too. If you want to, I'm here available to answer questions. If you want to stay in lab and grind it out, that's fine. If you want to wait or you want to check your work when you have either the pre-recorded video or this one, totally up to you. I just do the pre-recorded video because I have a number of students, like maybe 20% of the class actually doing this class asynchronously, remotely. And so I figured if I make pre-recorded videos available for them, it should be fair that you get the same thing. So if you want to do the lab, not necessarily during the lab period, that's why I make it available. But I still come to the lab one to answer specific questions and just to do it out. You might say that that's kind of, you know, butting your head, but again, I feel like you all paid for the in-person one, so I'm going to show up and do the in-person one. But the pre-lab one, you don't have to watch it. That's just if you wanted to get a jump, and if you had time this weekend over watching football or whatever, you are welcome to do the practice. That's why I do it. I understand everybody's busy and has got a lot going on, so if I can enable you with more information, thumbs up. If not, then you don't have to use it. Anything from TV land? I'm not going to stop recording. I'm going to pause it because it's just going to be not recording anything, but I can always restart the recording as necessary. Nothing? All right, I will pause and feel free to ask questions.